then look at a very simplified, discrete op-amp design, discrete being individual transistors. We'll look at the differencing amplifier stage and the voltage amplification stage with the ASU short. Then we'll look at the PCB I showed you at the beginning of this video, unit of multi-ring keycat. Finally, we'll use the Digital Analog Discovery Pro to do a real-world demo and tests of the real-world system to see how it performs and see how it performs in comparison with simulation. Thank you very much to Altium for sponsoring this video. If you'd like to try out Altium Designer for yourself, they're offering a free trial of Altium Designer if you go to altium.com/YT/FieldLab. Once you have your free trial, I would recommend checking out my SMU2 PCB design complete walkthrough for Altium Designer, which is a just under 3-hour video teaching you all the basics from the start of Altium Designer to get your product manufactured and produced. A big thank you also to JLC PCB for sponsoring this video. The PCB you saw at the beginning and the one I used to implement this discrete op-amp design was manufactured and assembled by JLC PCB in China. If you'd like to have this PCB made for yourself and try it out, maybe make some modifications, you can visit my GitHub account at github.com/GMS67 and navigate to the native feedback demo repository. Let's briefly go over the op-amp basics. Schematically, you will see op-amps drawn like this: a triangular package with 2 input pins with a non-inverting input plus and the inverting input minus and an output out. We also need to supply power to our device, and that typically is bipolar supply, but in our example I would just be using a single supply VCC ground. Essentially this op-amp is a difference amplifier. Whatever input voltage we apply across these pins is subtracted, multiplied by a very high gain, we'll call that A, and fed to the output. Op-amps typically also have a very high input impedance, seen at the input over here, and a very low output impedance in the output. As I said before, op-amps typically require dual supplies, so a positive and negative one with respect to ground, but we'll be using a single rail supply for simplicity. The governing op-amp equation is this one here. Our output is our very large open loop gain A multiplied by the difference in the inputs. This is usually enough to solve most op-amp circuits, but to get any useful circuitry with op-amps we actually need to use negative feedback. So we take some part of the output V out, divide it down by some fraction, and feed that into our inverting input because we want negative feedback, and we'll see why in just a second. An alternative view of the op-amp is this open loop block diagram, and hopefully this will simplify things a bit more. We have a difference in the beginning, simply subtracting V minus from V plus. The output of that is then amplified or multiplied by our gain. So we take our difference and multiply it by this constant A. Implicitly, our op-amp in the real world will have some sort of bandwidth, so some sort of upper limit of frequencies it can handle before the gain drops. The cutoff frequency is typically denoted in radians per second, and our conversion is simply 2 pi times the frequency in hertz. Now, as I said before, we would like to feed some part of the output back to this inverting input. And this is what we then typically call a closed loop system. We have closed this feedback loop. The way we do that is feeding back a fraction of the output, scaling it via this constant B, and then feeding it to the inverting input. B typically is a fraction between 0 and 1. The question is now, why would we want to do that, and what effects does this have? To do so, we require a tiny bit of maths, but don't worry, this isn't too complicated. We'll assume that we just have a single input for now, essentially that our non-inverting input V plus is equal to V in, just for simplicity, and we have a single output, which is V out, which is our normal operational amplifier output. We want to now find the relationship between the input and the output. So if we apply a signal to the V plus pin, what is the signal to the out pin? Let's start off by ignoring the bandwidth. So let's get rid of this block for now, and then we just see the output is A times the difference of the input. Minus, we set as a fraction of the output, which is B times V out. So we can substitute this expression into this. This is what I'm doing here. And then I can rearrange V out divided by V in, and we typically denote that by the gain. For example, if we have a gain of 10, we put 1 volt of the input, we'll get 10 volts of the output. It turns out our gain expression is this over here, A over 1 plus A times B. Remember, A was our very large open loop gain, and B was our feedback fraction between 0 and 1. This is all very good, but why is this useful? It turns out that the open loop op-amp gain A is actually very uncertain, but it is very large, usually on the order of 10 to the 5 to the 6. But this could be 2 times 10 to the 5, it could be 10 times 10 to the 5, so rather uncertain. B, on the other hand, is something we can control. We choose our feedback fraction. We say, okay, this is 0.2, we're feeding back with 0.371. So we can control demonstrate it very precisely. It turns out that if A is very large, looking at this fraction then tends to, as A gets very large, to 1 over B. So this is really cool because essentially our gain of this closed loop system does not depend on this very uncertain gain parameter A, which is intrinsic to the operational amplifier. So simply by varying our feedback fraction B, we can get a very precise gain of this closed loop system, so very precise amplification. This is pretty much independent of A, as long as A is very large. The nice thing is, this is not the only benefit of using negative feedback. It can be shown that negative feedback, the way we've applied it here, when taking an output, providing some sort of fraction back to the inverting input, it increases the input impedance. So Rin of the amplifier is increased, it increases the output impedance, Rout is decreased, it increases the linearity, so reduces distortion, and it increases the bandwidth of our amplifier. So this section over here. Just to show you why the bandwidth is increased, we can actually take the bandwidth into account into our equation. Simply, our output is now a function of frequency, and I'll just use angular frequency for simplicity, and that is omega. So we have A times the plus frequency gain with a certain nothing. However, operational amplifier, which essentially discrete operational amplifier of the signal, B to be you get ringing, oscillations, and an unstable amplifier. Because we have gain in this stage, we are capacitor and my power supply input, again a single supply, and I have my operation. Change the gain of the system as expected by root 2, and that is just under 4, I believe. So somewhere here is our new bandwidth, which is about 350 kilohertz. By increasing the gain of the closed loop system, I am sacrificing bandwidth. I can do that even to the extreme by turning the potentiometer all the way to the other side, and I get quite a lot more gain, to around 10 linear, but then of course I have a much lower cutoff frequency again, I know, something around 100 kilohertz. This kind of demonstrates the gain bandwidth product. So let's stay with this network analyzer and move our gain potentiometer right back to the center.